As we look at igneous processes, we have to consider Bowens reaction series. And this is how magmas, different liquid rock within the earth, can evolve. And we can go from having this ultramafic sample. Remember, the inner earth has a higher concentration of iron and magnesium. And as the rock cools, it's going to change. It's going to evolve. So one single magma can become a wide array of different types of rocks. And let's look at why. So how different igneous rocks form. It all starts in the mantle. The mantle is very hot. The mantle is composed of ultramafic rock, meaning very mafic. It is very dark in color. Plumes of rising rock in the outer or the upper mantle here, they're rising, right? Convection. Hot material rises, cooler material sinks. Cooler would be less dense, hotter would be less dense, and cooler would be denser. And these are mafic. And that means that they have a high concentration of iron and magnesium, and that should be reviewed. But not as high of a concentration of olivine as the mantle. That the mantle is going to have more darker, more ultramafic minerals than, say, the basalt, the oceanic crust. So once oceanic crust or basalt crystallizes, right, solidifies from a liquid, the evolution of rocks begins and takes off. Basalt is in motion, and plate tectonics helps tell the story. Because basalt is in motion, new rocks form as a result. And we can look at this. So let's look at basalt and granite, two of the primary igneous rocks that we'll study. If I look at basalt, I get this upwelling of magma. Really simply, it's just rising vertically due to being hot. And it cools on the Earth's surface. It is mafic and fine-grained crystalline. Right, fine-grained, cooled very quickly. So we would say that is aphanitic. This process occurs at ocean ridges. And where we see this ocean ridges is what it's called when we look at the Earth's surface. These are divergent boundaries. And we'll look at boundaries here in just a moment, which is a part of the Earth's ever-changing crust. So basalt is mafic, so it contains iron and magnesium, but it also contains lighter felsic minerals. That even though we see oceanic crust as being dark, it still has felsic minerals within it. It's just dominated by mafic minerals. They're the majority. So now let's look over here where we have oceanic crust colliding with continental crust, and this is what we call a convergent boundary. Granite results when oceanic crust subducts, and that's this process of subduction right here. Oceanic crust subducts beneath continental crust. It sinks beneath, and it can sink beneath oceanic or continental. But when oceanic crust subducts, remelting occurs. Remelting, right? The basalt is traveling back into the center of the Earth. It's getting hotter. So it's going to melt out the lower melting point minerals. So in this process, lighter minerals, the felsic minerals that have a lower melting point, they melt. And they rise in the Earth's surface, and we get volcanism. So this picture right here is of partial melting, and I think that's a key term you want to make sure you pay attention to. Partial melting. It's not all of the basalt that melts. It's only the felsic minerals due to the partial melting of basalt. So granite is the natural evolution of oceanic crust later on in the tectonic process. Let's go back to Bowens. Both processes, oceanic crust and continental crust, form. These are both the result of Bowens reaction series. So let's look at this. Lithospheric plates are moving. These are what we identify as a part of plate tectonics. This is a tectonic map. This is a boundary map. This is showing plate boundaries. And these are ocean ridges. These are what we would say, these are all divergent boundaries. That this side of the boundary is moving, okay, so this side right here is moving this direction. And at the same location on the other side, that's moving that direction. They are diverging. We're getting young, fresh, new, brand new oceanic crust forming right here at these ocean ridges along these divergent boundaries. So we're seeing here what's happening within the Earth's dynamic surface. And then this is kind of an artist's rendition of what's taking place. We have this hot plumes from the interior of the Earth, parts of the mantle rising. We have convection taking place. It's gradually moving along, cooling, and then eventually we would have this subduction here. And it's just kind of a cool picture. I like it, but it's kind of an internal rendition of what's taking place. So now let's talk plate boundaries. Now we're not going to do much with this plate boundary here. This is a transform fault. We'll disregard that for now. I want to look at divergent boundaries. Divergent boundaries. This is where we see this right here. Divergent boundaries where we are forming new oceanic crust. It's made of basalt. It's from these rising plumes of rock that come from the upper mantle. They rise up. They reach the Earth's surface, crystallize very quickly. This side is moving this direction away, and this side of the divergent boundary is moving this direction. But then we also have convergent boundaries. And convergent boundaries are where we have two plates colliding. Well, if this is moving this direction, if oceanic crust is colliding with continental crust, it's going to then subduct. It's denser. It's a mafic rock colliding with felsic rock. Felsic is lighter, In terms of density, mafic is heavier, right? It's a denser rock. It's going to subduct. That's a natural process. And in the subduction process, it's going to melt out. It's literally going to remelt out the felsic or the silicate minerals, excuse me, the felsic, the light minerals that are contained within the magmas of the, or excuse me, within the oceanic crust itself. So let's check this out. Oceanic crust forms as ultramafic rock from beneath the mantle, right? Or from deep within the mantle. It rises due to convection, and it reaches the Earth's surface along divergent boundaries. In this case, the rock basalt is mafic, so it is literally sweated or remelted out of ultramafic rock. Basalt forms from the partial melting of the rock from the upper mantle, right? Upper mantle is going to be ultramafic. If I remelt and I sweat out the less mafic minerals, it's going to be mafic instead of being so dominantly ultramafic. Whereas continental crust forms as oceanic crust subducts beneath continental crust, or oceanic crust. So if we find subduction, we're finding the partial melting of oceanic crust, and we are getting felsic minerals. Now you'll want to make sure you pay attention. This video right here is very, very key. I go through a lot of the video pieces that are very specific to what's taking place within the plate structure, the plate boundaries. You'll want to check it out. This here, convergent boundaries and subduction. So here I have the subduction, and I talked through this before, but I want to do it one more time. Oceanic crust is basalt. It is moving away from this divergent boundary here. It is colliding with another boundary here, another, in this case, continental crust. It's going to subduct. And this is where I find my temperature gradient. At these temperatures, you're remelting out the low melting point minerals that we find, that we call felsic. Felsic minerals here in just a second, I'll show you. You'll see that your felsic minerals have your lowest melting point. So as I reheat up basalt, it's going to get rid of itself. It's going to separate by melting the felsic minerals. And here's where this applies. Basalt, oceanic crust, this is what comes from the molten mantle that is composed of ultramafic minerals. As mobile magma upwells or moves upwards, right? It's moving vertically. Some of the ultramafic minerals crystallize out, leaving only mafic minerals. So here's what I'm saying. So let's look at this picture here now. Bowens reaction series, and here it is. If I have peridotite, which is a common mineral, a common rock that's it's composed of olivine and calcium-rich plagioclase. That ultramafic, and we can talk comatite or peridotite, but peridotite's more common. These rocks are comprised of olivine and calcium-rich plagioclase feldspar. Well, if it loses olivine, it's going to be then mafic. It's going to be mafic. It's going to have a little bit of olivine. See how this arrow just barely reaches into the mafic realm? When I say mafic realm, I'm looking at this kind of square right here. And basalt and gabbro, right? Basalt, oceanic crust, is dominated by pyroxene and plagioclase feldspar. And it has some olivine, a little bit of iron, a little bit of olivine. That's just going to have a high dosage of iron and magnesium. But so does pyroxene. This is dark mineral. And your plagioclase feldspar is actually, it is consistent with, always found with pyroxene. That's because mafic minerals, these are the temperatures in which they crystallize or solidify out. So let's go back and look at this temperature gradient here. High temperatures, olivine and calcium-rich plagioclase, these are going to crystallize out of an ultramafic, let's just say an ultramafic magma. As it's cooling, right? As it's cooling, these solidify, and because they are denser than the surrounding material, they're going to fall out. So you're going to be subtracting olivine and calcium-rich plagioclase from that magma chamber. And be sure to watch the video that I load that I'm going to talk you through an evolving magma. I'll show you that in a little bit. So back to pyroxene and plagioclase feldspar. Once I have this mafic rock of basalt, if that magma keeps on cooling, pyroxene and plagioclase are going to settle out because it is going to cool below its melting point, right? This magma is cooling. And so if I have a mafic magma and I get rid of pyroxene and plagioclase feldspar, I'm going to be left with the remaining melt is going to recrystallize itself. The chemistry keeps on taking place. And it's going to kind of orchestrate the silica and the oxygen and all the remaining iron and magnesium, and they're going to be forming amphibole, biotite mica, and you're going to have some plagioclase left over that's going to be sodium rich. And those are the constituent minerals within intermediate rocks. Intermediate rocks will have amphibole, maybe a little pyroxene, biotite mica, and sodium-rich plagioclase feldspar. And if I continue cooling that, notice I will continue to evolve this magma chamber, and I'll only have left, because these will solidify, crystallize, and settle out, I will only have felsic minerals left. I will have K-spar, potassium feldspar, muscovite mica, and quartz. So therefore, if I have one magma that eventually cools very slowly, it can go from being ultramafic, and it can end as leading to a felsic, it can lead to granite. And that's a very unique situation. In this case, Bowens reaction series makes sense of all that. So let's put it all together. I have this high temperature magma, right, 1200 degrees C, as it cools down to 750 degrees C. I can look at this as the higher temperature, this olivine is a higher temperature mineral. So as it cools down to, say, 1100 degrees, I'm going to lose the bulk of the olivine and a lot of the calcium-rich plagioclase. If it continues cooling, I'm then going to be settling out the pyroxene in the plagioclase feldspar. If it continues to cool, I'm losing amphibole, biotite mica, and your sodium-rich plagioclase. And then lastly, what I have left over is going to then be left in the melt. It's going to be K-spar, muscovite mica, and quartz. So that's just a further rendition of how we can go from ultramafic to intermediate to felsic as the temperature of the magma cools. So minerals that crystallize at high temperatures are rich in iron and magnesium, and these are ultramafic to mafic. Minerals that crystallize at lower temperatures are felsic minerals, and they are low in iron. They can even lack them altogether. So intermediate rocks can be found within specific minerals, such as, intermediate rocks, here's the crazy part. Intermediate rocks always contain biotite mica, amphibole, sodium-rich plagioclase, and maybe just a sprinkling of pyroxene. Whereas all felsic rocks contain K-spar, muscovite mica, and quartz. And you can get a little bit of a dabbling of B mica and tiny amounts of amphibole. And whereas all mafic rocks contain a large amount of pyroxene, a little bit of olivine, and dominated by plagioclase feldspar, maybe a little B mica and amphibole. So the Bowens reaction series is showing you the evolution of a magma. So when we put it all together, an ultramafic magma can become a wide range of rocks as it cools. So we can apply Bowens reaction series to see how this occurs. So we can actually apply this concept, and if I look at the chemical structure here, or the crystalline structure, olivine is my ultramafic mineral, right? Magnesium, iron, remember, it's still silicate. But these are the simplest structures. These are a single tetrahedron. That these separate first. And if these are within the liquid magma itself, they separate, they sort themselves out. They sink. They are high in iron. But then the chemistry, the leftover magma, has a little bit more time to evolve. So I could say that the pyroxene, which is augite, has a little bit more time to kind of re-network itself and become a little bit more complex. So these are single chains. So instead of being individual crystals, they're going to be in chains. And if I separate out my pyroxene and augite, all of a sudden I've changed the chemistry. Now it's going to form amphibole. These are double chains. These are just a more complex evolution of that very magma. And I can get this mineral here, amphibole, and sometimes I get sheets. These are my B mica, biotite mica, and my muscovite mica. It's simply using the remaining, the leftover of what's in the magma. But notice, because it continues cooking in its chemistry evolution continues to take place, it gets more complex. Here we go, single tetrahedron. Here we talk chains. Here we're talking double chains. Now we're talking sheets, right? We're always talking sheet. Always. And then last but not least, the most complex networks are your three-dimensional networks. And this is what, these are my felsic minerals. Felsic, here's my K-spar, here's my quartz. Orthoclase feldspar, plagioclase feldspar, and my quartz. These here have the three-dimensional networks. They've had the longest time for the heat as the magma cools to evolve into a much more complex three-dimensional network. And there, people, as we say in the rock world, there you have it. Yee-hoo, dog!